To lunch. This session is all about doing proofs at scale and addressing side effects like brittleness that come with it. The next talk is going to be by Jaloyan from Amazon, and he will talk about enhancing proof stability.
Thank you very much. So hi everyone. So I'm George. I'll be presenting you some nice work I did with Xiang, Jenny, and Florian on how to make Dafny proofs more stable. So the claim, which is extremely intuitive but actually not that simple and quite interesting, is that simple proofs tend to be less brittle, so they break less often. I'll detail a little bit more what we mean by simple proofs and brittleness. That is the whole point of the talk. So let's start with Dafny. So a little context on how we are using Dafny in our team at AWS. So fundamentally, we are doing and rewriting the whole core authorization engine. So this is some Dafny code for which we have written some spec. We have written also an implementation. We check that the spec is the same as the implementation, that implementation verifies the spec using Dafny fundamentally. So this generates some Z3 queries that are then discharged using the Z3 SMT solver. And the implementation is then compiled to a Java implementation and code that will be the one that will be running in real production. So to give you an idea of the scale of what we are dealing with, so fundamentally the specification and implementation altogether is about 17,000 lines of code of Dafny. The Java code that we are generating is about 3,000 lines of code. And the very interesting thing is that this Java code is running at 2.3 gigahertz. This means that the code is being invoked 2.3 billion times a second. So the scale is absolutely huge. We cannot afford any mistake, so you can guess that this is absolutely critical code, and it needs to be scaled and extremely efficient. So we are due to this constraint, so the code is really made to work fast, and we are transferring all the burden of verification on the proofs. So we prefer having more complex proofs at the expense of, we have simple implementation at the expense of complex proofs. And to give you an idea, we have about 15,000 verification conditions that are generated. And the biggest verification condition is in the order of 9 gigabytes. So we have an SMT query that is 9 gigabytes big, and we have to send it to Z3 to deal with. So as you may have guessed, when you have 9 gigabyte query, what happens is we have what is called proof brittleness. So Z3 uses a lot of heuristics, a lot of backtracking and different things that make it sensitive to changes that may be minor or unrelated, and we may switch if we switch the different version of the tool or upgrade to another Z3 or change Dafny version or just do a minor unrelated change, what happens is potentially the proofs may break. So this has been predicted of going to scale with verification tools, and this is exactly what we are dealing with. So to give you some little metrics, so each time that we had upgraded some tool, so be it Z3, be it Boogie, be it Dafny, we have at least one VC that was broken. So each and every of our updates went bad. So we had to spend some time to fix it. On average, it was 5 verification conditions that were broken on each update. Of course, the consequence of this is now we have to spend some time to fix the proofs and re-establish their validity. And this blocks us from shipping new code, from working on other features. And usually it's in the order of a few days, but it can go as much as 14 days. And of course, because of this instability in the proofs, so we had to forego some of the changes that we were planning to do because the proofs were just too brittle, and we said, well, we're not going to implement this feature or this very minor optimization because the proofs are becoming so brittle that we'll not be able to maintain them anymore. So this is a problem. We need to find a solution. So what may be causing brittleness in our situation? So there is some environment issues. So for instance, if we change the ISA, like Z3 compiled on R64 and Z3 compiled on x86, are not behaving the same way. So on same queries, they may give different results. Same for operating system. We have seen some differences in different operating systems. Then there may be the tooling, like Dafny versions that may not be the same, Z3 versions that may not be the same, some libraries that may not be the same, and proof hardness, which is usually what we think about when we're talking about brittleness. For instance, we have huge SMT queries, like with many unnecessary facts in context. We have function bodies that are visible to the caller, again, adding some additional data and facts that may not be necessary to do the proof. This leads to huge SMT queries, and sometimes with complex theories like mixing arithmetic, set, and this kind of other theories may make the proof the task harder for Z3. So the first two are, I would say, not easy, but like quite manageable, because it turns out that we are a cloud company at AWS. So environment and tooling is exactly what we're able to provide. So there will be a talk this afternoon on like the different solutions to mitigate those two problems. So just follow Eric's talk. And the thing that we'll mostly focus on in this talk will be the proof hardness part. And there is no way to cut the corner. We just have to make simpler proofs here. And this is exactly what I'll present. So this is Dafny'24, which is a coding style for Dafny to make the proof simple. So what is Dafny'24? So let's say what makes a proof simple. So there are mostly two metrics that can be used for measuring the complexity of a proof. So the first one, is using the flag isolate assertions, which will allow us to measure for one VC at a time the different metrics, because Dafny bunches the verification conditions together, so it's hard to measure anything. So we have to separate them. Once we separate them, there are two things that we measure. So the first one is called the resource count, which is defined with the flag resource limit. So this is a metric that is used by Z3, which aggregates a lot of internal elementary operations that Z3 does, and this is just a measure of how hard it was for Z3 to discharge the VC. And the second one is the elapsed time. So this is just how long it took for Z3 to solve the issue. If we look, actually, so this is a graph, a plot of the resource count on the y-axis against the duration on the x-axis. We see that this is quite correlated between the time and the resource count. And we see that harder proofs tend to take more time, be it in resource or be it like in duration. So instead, we'll use just the resource count for now. So we'll just focus on this. The idea of Dafny'24 is to limit as much as possible the use of SMT automation. So our goal is to make sure that Z3 has a very low resource count so that it does not do a lot of work. And our claim is that if we manage to discharge discharge Z3 from a lot of its burden, then we could have proofs that break less often. So how do we do it concretely? So I'll give two little examples. So first one, this is the first focus. The idea is to make everything opaque. So like if we look at a very simple example of code, so this is just a while loop iterating on the variable I that has been initialized at 0, and we iterate until a value that is named foo, and we do some stuff in the while loop. So usually the way we would prove this would just be writing an invariant and let Dafny do the job. So it's extremely great at automating this. So usually that's what happened. We just write the invariant and that's it. What we're doing instead here is marking the invariant as opaque instead, which means that its body will not be available to the loop when it will try to prove. So the proofs will fail because we need to do the proofs by hand now. And what we'll have to add instead is two lemmas. So the first one is invariant initialization, which will ensure that the invariant holds at the beginning of the loop. And we'll do the proof in the three dots by hand. So we'll write literally a set of assertions that will help guiding the proof. And same, once we reach the end of the body of the loop, we'll have to show that the invariant is preserved. So we have another lemma for that we'll invoke, which will require that the invariant holds at the beginning of the loop. And it ensures that the invariant holds at the end of the loop with the new value of I. So this is exactly how we would do the proof by hand. So if I were giving a lecture on how to demonstrate an invariant, I would literally like do those two proofs by hand. So this is what we are doing. Second idea is to remove post conditions altogether from functions. So here it's like an implementation of the min function that you can see on the left side, which is how we would write a min function. So it's just a function that takes x and y as parameters that returns another integer. And if x is smaller than y, we return x, otherwise we return y. And we ensure the three conditions for being a minimum, that the minimum should be lower than the two parameters and it should be equal to one or the other. The Dafny'24 version instead removes all the ensure clauses. So we totally take out of the ensures to make sure that they do not get added to the context when I call this function. And instead, I'll put them as a separate lemma. So each time I need to know that the min will give me the minimum of the two values, I will call this lemma, which will ensure me exactly the post conditions. And how do we guarantee this lemma? By revealing the mean function, which will help Dafny prove it. So by separating the contract and the implementation, I can control with much more precision. I can control what I add exactly to my context. So it's almost as if I was doing the proof by hand. So each time, at each point of the program, I know exactly what is in the context and what is required to prove each assertion. So does this make the proof simpler? So this is the graph of resource count against time for one of the modules that we have rewritten in Dafny'24 style. So this is the most complex module of authorization, which is the string handling. So we have rewritten it in Dafny'24. So this was before in normal Dafny. So you can see that resource used to go up to 10 to the power 7. So there is a 1000 factor between Dafny flag in resource count and the Z3 resource count. So this would be equivalent to 10,000 in resource count. And once I plot the Dafny'64 version, so here you can see in green, I managed to reduce by 2 orders of magnitude the resource count used by Z3, and also by about 2 orders of magnitude for the time, similarly. So yes, the proofs are simpler. But does this make the proof less brittle? So now let's discuss about a little bit brittleness. So brittleness, as we have seen, is characterized by the fact that when I have a minor change anywhere in the code, some unrelated proofs may break. Same if I change the tooling. So Dafny reference manual has been giving a very good guideline on how to measure brittleness, and there is a feature called the random seed. So the random seed changes the SMT query that is being sent to the solver by changing the ordering of the SMT commands, the variable names that are used, or the random seed that the solver uses when it's making arbitrary decisions. And actually, this is a very good proxy for like those kind of breaking changes, because when I upgrade the tool, I'm not expecting something to fundamentally change in the generated VCs. The thing that may change is mostly the ordering, the variable names, and this kind of minor stuff. So actually, this is a very good proxy for measuring this, for simulating this kind of change. And Dafny has been giving a guideline. So for this, it's quite arbitrary, but it proved over experience that it works well to measure brittleness. So we attempt each proof using like different random seeds. So we use 5 here, which is the good compromise. And then for each verification condition, we have now 5 different resource counts that have been computed. And we will compute the coefficient of variation of those resource counts, which is defined as the standard deviation divided by the average. And this gives us a coefficient between 0 and plus infinity. And if this coefficient of variation is greater than 0.2, then we consider that this proof is brittle. So this verification condition needs to be reworked to make it simpler. So does Dafny'64 reduce brittleness? So this is the histogram of the coefficient of variations that are measured for the same module that we have rewritten. So you can see that like if we look at 0.1, so we have the 1.0 to the power 0, which is like everything that is under 1 and greater than 0.1. So we have about like 100 proofs that are in 100 VCs that are in this category, out of which about like 50 are really brittle. This means greater than 0.2. So we see even one that is like greater than 1 and lower than 10. So there is quite a lot of brittleness in the code base that we worked on. So once I rewrite everything in Dafny'64. So this is my new histogram. So as you can see, like I managed to reduce significantly all the coefficient of variations, all the brittleness, and the max that I have, there is only one VC that is at 0.1 of coefficient of variation, which is still under the threshold of 0.2. So we managed to like remove all brittleness from our like code base here. On the drawback, so a little bit some explanation on the code size impact. So this string processing library has 2 functions. One is string splitting, and the other is shell glob matching. So those are like 2 main functions that are in this library. And fundamentally, before in Dafny, the string splitting was 150 lines of code. And in Dafny'64, it's 50 lines of code now, because like we took out all the specification and moved it somewhere else. And now instead we have 18 lemmas that are about 220 lines of code. So we have a slight increase in the code size. And for shell glob matching, it's also exactly the same. So we used to have 300 lines of code with 15 lemmas that were 350 lines of code. And now it's only 80 lines of code with 31 lemmas of 860 lines of code. This is actually like there is a little like unexpected good outcome, which is now the code is much simpler. Now that we have taken all the spec in a separate file or lemma or separate module, now actually the code is much simpler. So when we read the code that is really doing the real code, the real non-ghost code, actually we can be able to much easily understand what is happening. And conclusion, so we have seen that simple proofs indeed are less brittle. And Dafny'24 helps reducing brittleness on large code bases. And as future work, what we may do is maybe automate Dafny'24 and have it as a style checker. So it would be nice if we could do Dafny ---- Dafny'64, and automatically it will check for all of these. And we still have to use the resource limit to play with the resource limit to find another cutoff value. So we took 100 here as an arbitrary value, but we may expect that actually maybe it's 200, maybe 500. So we need to play a little bit with this. Thank you very much, everyone. So if you have any questions.
Thanks, that was really interesting. I was wondering, you said at the end that maybe there could be an option for doing the Dafny'64 checks automatically. To what extent could the transformations be completely automated? And for example, could this actually be part of Dafny behind the scenes? Behind the scenes, it will reorganize your annotations in a more SMT solver friendly way, but give you the freedom as the programmer to write whatever you like the best.
Some parts of it may be automated with some analysis, like for instance, all the reveal statements that we're adding. Maybe there may be some analysis or like building some trees of dependencies of assertions to be able to control more finely what is exactly revealed. But some other checks that were like some of the rewriting that we have been doing was also related to changing the types that we're using, or like things that may be like less automatable, like some of the things that like totally rewriting, like for instance, there was one for loop that we had to write in another form, and like instead of having a break statement, we had to instead like have an assignment with a return. So those things may take a longer effort to automate.
So it's not a completely mechanical process. There's some creativity required.
Yes, we spent quite a lot of time to be able to like reestablish all the proofs in Dafny'64 style.
In the example evaluation you showed with the lines of code blow-up, what about clients that use those verified modules? Like now they need to invoke those lemmas. Do you have a sense of how much that changes the proof burden for clients of those libraries? Or are these not really clients that have libraries that have end users?
There is only one client, which is like our library, our authorization library. So this is the part, a small part of the authorization library, which is the string handling and string processing. The thing is calling those lemmas, that's one of the main points when we had to repair all the proofs, because now everyone who calls those do not have access to the context anymore. So the strategy we used mostly was each time that we're calling one of those nodes, we're literally revealing almost everything immediately after. So this is not optimal. So the Dafny'64 is really well designed for a small part, and now we are extending to the colors slowly. So now we are revealing everything, and there is way better solution than just revealing everything immediately after the call. So, yes.
So you suggested that you should remove all post conditions. How does that work for methods? Do you only have functions?
No, we have, I would say, only methods. We have very few functions.
Okay. So how do you do the part, because methods are opaque, but you can't reveal them inside another method, right?
Yeah.
So how do you do the verification of the post conditions of the method if the method definition itself has no post conditions?
There is function by method that we are using for some of them. And then for methods, what we have is we have like imperative implementation, and we have a functional implementation, which is the spec, fundamentally. So once we know that the method satisfies the spec, then once we give the spec to the caller, it contains enough information not to be able to know what's inside the body of the method.
All right, thanks.
So you are advocating for this new style of writing Dafny code. Would you say that the -- Dafny'64 mode should be the default So the other way of asking the question is, are there some libraries where it's more preferable to use to allow everything you forbid rather than using your style?
It's a trade-off because like using Dafny'24 style makes it like you control much more what you are adding in context, but you spend more time writing everything. So if you are writing a small library in which there is no scale issues or like brittleness issues in the proofs, like don't use Dafny'24 in this thing, because like Dafny is really good at automating things, so you want to leverage this. And this is mostly like when we start having like scaling issues and brittleness issues, that's where we had to control manually what we are doing in the proofs, and this is where Dafny'24 really comes handy. But yes, for large code bases, I would advocate for Dafny'64 by default.
I think we have to move on. So let's thank George again.
Thank you very much.